Nice. All right. Well, which screen are you guys seeing? Are you guys seeing the full slides or the sectioned one? I don't really know what's going on.
The section, not the full slides. So
Oh.
we're just seeing the
How do you know how to
one
make
that
it?
your view. Yeah. So you just have to choose the screen that is the full slide. So you got to
Oh, I
present
see.
first.
Got it. And then share the right
Present,
screen.
yeah, present. Yeah, exactly. And you
Got it.
can present or preview. You can get access to your windows.
This works. All right.
Yeah, that's perfect.
All right, cool. Yeah. So so today, for the next, kind of 30-40 minutes, I'm going to talk through this relatively complex Jac program that I've built with Jason's help over the past few weeks, mainly in the interest of delivering to HLP, but throughout the process, we're able to extract a common infrastructure that we call CannoniCai, canonical conversational AI architecture. That the purpose of it is, something we're able to use to as a solid foundation for us to build other conversational AI and chatbot kind of experience for other use case very easily in the future. So today I want to walk you guys through some of the design that I've done, and hopefully this will be helpful to everyone, especially considering everyone is getting to build their own Jac at this point. So a quick agenda. I'm going to first do a quick architectural overview of the. It is recording, right? Is it recording? Yep. Okay.
Yes,
I want to do a quick architectural overview of kind of the main components of this program. In the process, I'm going to talk about a few design principles that I was kind of following as I was designing it, and then we'll just deep dive into how this CannoniCai program come together, right? The various nodes and edges, what water is being used, and how we're currently handling dialogue management and context retention, something pretty important for any kind of sophisticated conversational AI experience. And then I'm going to touch on how we did kind of like a multimodal conversational AI structure with the traditional, dialogue oriented conversation combined with an FAQ based conversation, how they're able to kind of interact with each other. And then I'm going to touch on how, this type was AI model, how we're able to integrate training, testing, and deploying the various AI models all together into within the Jac program, so that you have a one-stop shop that for you don't need to essentially leave Jac or leave GSCTL for you to build something end to end. And then I'm going to quickly talk about the testing setup we have and some of the future kind of improvements that we're already thinking. One thing I want to say, this is something that is constantly evolving, right? Like this, what we have here is already very different from what I have originally started. And there's already, when we get to the last future work section, there's already a few things that we know we want to improve. So, what I hope this will achieve is serve as kind of, half of reference, half a inspiration for everyone here to, as they kind of embark on their journey of, if you guys embark on your journey to build your own conversational AI, kind of chatbot intent and all of that, this serves as inspiration, right? And also, if you wonder how certain things, if you wonder where to start, this perhaps can serve as a reference. So just real quick, what is, CannoniCai, or this canonical conversational AI program we're trying to build? The goal of this is we're trying to build a generalized or canonical conversational AI infrastructure that can enable us to build out sophisticated conversational AI experience and products very flexible and with a lot of ease in the future, right? HLP is kind of our first customer that we need to do this for, but we want to take this opportunity to build something that we can leverage for the future, right? We want to do the heavy lift now, and we can replicate easily for the future. And kind of one of the objectives that I had, and Jason was kind of urging me to do is having this program and having Jac and having JSCTL to be the centralized place where you do everything you need to do to build out this experience. That would include, training and testing your AI models, defining your conversational states, your dialogue management, we're managing, specific user data, right? This time the user, in this context, the user being the person that's actually talking to the chatbot, right? And then have it to be modular and set up in a way where you can add custom logic that are, specific to each individual capability you're trying to build, and then also be able to flexibly customize the response that you eventually spoken back to the user, right? So it's the goal here is you don't need to leave Jac, you don't need to leave JSCTL in order to do all of this. And starting from nothing, starting from this foundation, being able to build whatever experience you're trying to build. So this is a quick, architecture overview, a 10,000 feet view of the graph, which represents the scope of capability that you are able to do with this Jac program. There are, it's very colorful, right? I made that intentionally so that it's not that boring to look at. But there's also, there's a lot of different pieces, right? So the way I structured this presentation is I want to do a breadth first approach, where I want to touch on these individual main components, give you guys an overview of what these things do, highlight some of the key properties, some of the key workers that you can use to interact with each one of these components. And then, so that I want to, after this talk, what I hope I will able to achieve is everyone can jump into this program and just Jac code and are able to, navigate your way through. It's like, oh, I wonder, how Yiping did the FAQ piece. You'll be able to know where to go to and, navigate the source code with relatively ease, right? And then, if we need to deep dive into individual component, I can pull up the code and we can do that. So on this graph piece, right? So there's basically four or five, depending on how you look at it, main components. So there's the conversational states. So this is the majority of the logic. This is where you define your conversation states, this is where we handle our dialogue management. We'll go into details how that's being done. And this is where you specify, the various capabilities you want to build. So if you want to build, a grocery purchase chatbot, right? This is where you have, a ordering state, a payment state, a confirmation states, and connect them with various edges, so on and so forth. And then on the same time, we have this FAQ state and architecture that also serves part of the conversational experience, but it's of different nature than the one on the left. The one on the left is mostly for conversation, right? It's for complex task-oriented or goal-oriented task that you're trying to achieve. You're trying to perform an action, or you're trying to get a specific answer out of a very complex question. While the FAQ part is more about simple one-off one-turn kind of question answer interaction. So something like, what is in the context of HLP, right? Something like what are different type of loans, right? What are different what is my credit score, right? So they're built slightly different, and that's because they're designed for different conversational interaction. And the reason I want to highlight this is because these are multimodal, right? So two different conversational type we're handling with different worker, with different logic, with different design patterns, but they are able to work together because they're all connected in this one integrated graph. And we'll get into details of what that means. And then on top, we have several nodes that are designed to help you manage your AI models, right? So this is where you go to train, to test, to evaluate, to deploy your AI models. And then, and last, we have a set of user management nodes. So this is where you store end user specific data. And this is also how we use to achieve context retention across dialogue terms. So what I mean by context retention is a pretty common term in conversational AI domain. But so what context retention means is, if you're talking to, let's say you're talking to Siri, right? It doesn't really remember, from question to question, it doesn't really remember what you asked before, right? But if you're talking to a human, they would, right? So let's say I'm talking to Ashish about something, right? I'm like, hey, like I say, I'm telling him about my travel plan, right? I'm gonna travel to India next week. And then the next question I say, oh, how much it is generally to stay there at a hotel, right? As a human, you remember, oh, I just talked about traveling to India, so this hotel lodging question should be relevant to that. So that's remember what the user has said previously, so that it can influence the processing and understanding of the upcoming request and question. That's what context retention is. It's a key piece of creating a really exciting and intelligent conversational experience. So that's the graph architecture, and there are a few design principles. Right? I'll run through this relatively quick because they're pretty high level and vague, and it doesn't really mean anything until we get into details. But there are a few design principles. So we wanted this this canonical infrastructure to be as modular as possible, and really leverage the data spatial programming nature of Jac. And these two actually comes hand in hand. Is and I'll highlight where we're realizing this. It's because of the data spatialness of how we design this program. How we design the node and ability and the workers. That's how we're able to make this thing really modular. And I'll tell you exactly what I mean. And then be able to support different type of conversational AI architecture, right? So I mentioned earlier, there's the traditional, turn-by-turn dialogue-based conversation, and then there's the FAQ based conversation, and we can imagine expanding to other type of conversational AI architecture, having them coexist in the same ecosystem. And then being able to achieve flexible and robust dialogue management. So this is the context retention piece that I talked about. And then last but not least, being able to have this program to facilitate a complete end-to-end AI model development flow, right? From data collection to training to eval to testing to deployment. So with that, I want to give kind of first is introduce the important nodes and edges that we have in this program. So on the node side, so there's more to what's on this slide when it comes to nodes and edges, but I'm highlighting the important ones that we're going to use throughout this talk. And once you understand these ones, the other more supporting type will fall into place pretty easily. So so we have state, which is the main conversation state, and then we have FAQ states / FAQ answer states. So those are the states or the nodes that we're using for the FAQ part of the graph. And then we have, and then there are specific AI engine nodes. So these are the node that we will go to train and test and evaluate specific AI models. So in this context, we have one for bioencoder, we have one for Flare NER, and we actually have another one for transformer based NER. So the work that Ashish and Satyam, you guys are doing, it's come to fruition here. And then we have user DIR, means user directory, and user nodes that are for the that are they're for the user management states, and they are connected through the various edges: transition, FAQ transition, FAQ answers, and there are a few miscellaneous ones that aren't as important. So okay, now we're getting into the nitty-gritty, right? So state node. So what is the state node? State node represents a conversation states. So that means so that's a state that a user can arrive at or start at any given point, right? So this represents where a user are in their interaction with the conversational AI agent. And majority of the logic of this CannoniCai infrastructure live within the node abilities of the state node. So I'm having a screenshot of the code here. Obviously, you can't see any details, but in the next few slides, I'm actually going to walk through these key node abilities and how they come together to make this flow of conversational AI journey.
Can I dovetail in there just real quick? Yeah, so this is, first of all, this is awesome, super awesome. I wanted to point out though, for Eldon, so Eldon actually started using the inheritance capabilities, the multiple inheritance, the overloading and overriding capabilities in Jac. Those capabilities was inspired and prioritized because of the journey Yiping went on with the logic you're about to see. Now, I actually think it'd be super cool, Eldon, if you could show how you're using your not polymorphism, but how you're using your multiple inheritance, because you can, and as you watch Yiping's implementation, you can see where, Eldon, I'm sure you'll be able to see where, oh, you totally need that inheritance. So maybe we can do a little bit on that inheritance stuff next week, Eldon, if you're down.
Yeah, sounds good.
Yeah, man. Awesome. All right, cool.
Awesome. Yeah, the first bit I have in the future work is node inheritance. As I'm putting together these slides, I realize like there's so many places it can be useful. But yeah, so one thing I want to highlight here, right, is the majority of the logic of this program exists in these node abilities. The walkers, we really have like 2-3 walkers that you use to interact with this thing. The walkers are very thin. There is really barely any logic in the walkers. And the reason that, to be fair, when I started, it wasn't like this. When I started, a lot of this stuff, a lot of logic were in the walker, and the node were basically data storage, entry. But, Jason was nudging me to like use node abilities. And as I'm kind of transition towards that, what I realized really nice about node abilities is it made things, it really realized this data spatial kind of programming kind of nature. And you essentially, you're defining your logic close to the data that the logic needs. And what that will enable you to do is make things really, really modular. So you'll be able to take, all you need to do is take the node, and if you want to re-architecture your conversational flow, right? Let's say, we actually have this problem with HLP right now where, we have this micro flow of like several states. Right now is, chained after another capability. So you have to go into that flow and then go into this micro flow. But we want to hoist that up at the root level so that you can access it anytime. Because the specific logic for the node are stored in the nodability and are part of your node definition, all we need to do for that to happen is just literally change how we define the graph. Instead of this microflow, instead of changing the edge, instead of connecting to this other capability, we just connect it to the root. And obviously we need to add more training data, but in terms of re-architecting your program, that's all you need to do. And it's because the abilities are embedded within your nodes, and you can take them wholesale and then just move it to wherever you want. And the water logic doesn't need to change because the water doesn't have any logic, right? So, for the next few slides, I'm gonna take you on a journey of life cycle of a request, and how a water traverses from node to node. And the few notability I want to highlight here is these 5 here. So listen, plan, think, speed, and cleanup. So these are where majority of the logic are, and the various other notability you see here, collect intent, classify intent, these are essentially invoked by these abilities. The main water that you're going to use to interact with the conversational experience is this totter water. So this totter water takes in the question from the user, and it hops from state to state and trigger the various node abilities to apply natural language understanding to parse and process the question, extract useful information, and process any custom logic. You might need to call third-party API, do any kind of custom processing, and then generate a natural response to be spoken back to the user. And as you can see, what's on the screen is all of the water logic. None of it is even hidden, and it's very simple, right? Outside of the variable that it needs to keep track of, it's really just all it has is going from state to state. It's because the logic are in the node ability itself. So I'm going to take you on this flow, right, of a example question on this example graph. This example, you can imagine a chatbot where it has this 3 capability: asking about weather, asking about directions, and order an Uber. Right, it's a very simple example, and imagine the user asks the question, "Hey, can you order me an Uber? I'm going to be late for work." For the next few slides, I'm gonna kind of take you on this journey of how this water robot go from state to state and trigger the various abilities at each state to do the necessary processing for it to finish the request and return response to the user. And then we're going to keep throughout this, we're going to keep track of this dialogue context table. This is something that the worker is keeping track of. And at various nodes, the node will insert and remove information to this context as necessary. So when the request comes in, the water robot starts at the root node, right? The request comes in, you don't really know. Imagine it's the first time the user asks a question, you don't really know where it's supposed to start, so you start at root. And so this is where the first ability that's triggered called listen. So in listen, all it does is it's doing the class. This is where we apply like the NLU engines, right? So we're classifying the intent. We're trying to figure out what the user is trying to do, and then we're applying entity extractions to extract useful information, the useful words and phrases out of the incoming question, right? So and then we update what we extract and understand into the context of the worker. So in this case, we're able to identify intent being order an Uber, and in this case, there's no entity that are interesting to us in this question. Then the results are saved to the worker context, right? So the node are still stateless, right? The node doesn't know the worker was here. Well, the node knows the worker was there, but we're not touching any of the specific states that are part of the node. Everything that is specific to this interaction, to this dialogue session, are saved in the worker context. So that's listen. After listen, the worker is still at the root, the node is started. The next step is called plan. So this is where based on the previous NLU results, we're going to decide where the worker should go to next. So this is where you build out your kind of conversation graph traversal logic, right? So in this case, we have a simple classification kind of based transition where based on the intent we're predicting, we define the destination state, which is the state that the robots needs to go to, and then save that to the worker as well. So also at this point, the worker hasn't walked yet. The worker is still at the root node, but the node is telling the worker, hey, you need to go to the Uber state next, because based on our analysis, that's what the user wants to do. And the next is take. So now the control is back to the worker. And this is really the only thing the water does, is it's just take the destination state. So based on what the node tells me to do, I'm gonna traverse that state, right? So the water will go from root, follow this intent transition, go to the Uber state. So now the water is at the Uber state, and then we have this little auto scope handling here, where if the water can't find or can't get to the destination state, will provide a default response of, hey, I can't handle that just yet, right? So this kind of catch-all, if it's out of scope or there's some kind of error, you don't end up with a broken thing. You still have somewhat of a natural response. So now the water is at the state that's corresponding to the question asked by the user. So we're at the Uber state. The next step is, we're back to the node abilities, right? The next step is think. So this is where you conduct any state specific logic through this business logic capability. And so this is where you call any third-party APIs, query any custom database, any kind of processing that you need to construct a response or finish the task. This is the business logic abilities where you would do it, right? So in this case, perhaps the logic will be talking to the Uber API and make sure you have you're logged into Uber or something, right? And then after think is the last step is speak. So this is where you already done your business logic, you already performed the task or get all the information you need to get to be able to respond to the user. This is where you construct a natural language response to respond to the user, right? So that happens in gen response, and then you're reporting that back through the report keyword as part of this node ability. So at this point, most of the as far as the user concerned, the request processing has already finished, and we have a last step that's called cleanup. So this is where we'll do any kind of maintenance, any kind of graph update post response based on what just happened, right? So this is where we can achieve context retention. You can customize your dialogue management logic. A lot of it can happen here. So you can use this cleanup to save any context you wish to retain for any future conversation terms, right? So for example, you can save that, in this case, the user asked for Uber at 9 a.m. on a Thursday. So perhaps next time you can use this piece of information to proactively prompt them, hey, last week this time you ordered an Uber. Do you want me to order an Uber for you now, right? So that's just an example, right? But basically, this is where you can retain any relevant information you want to save that are generated or processed as part of this conversation term. And the way that we achieve that is if you look at this, is actually a really interesting piece of logic. So as part of this node ability that are triggered by this talker worker, we're actually spawning another worker called maintainer. I have a different robot. I thought the robot was pretty cute. You launch another worker called maintainer, and the talker worker pass into the maintainer worker the relevant context data that it wants to save, right? So in this case, you see there's user, if you look at the code, there's user context, dialogue context, as well as the state that I'm currently on, right? I'm passing the talker worker are passing all of that to the maintainer worker, and the maintainer worker are traversing to this other part of the graph that have all of the user information stored, right? So, the user node, the next slide will tell you what the user node is, but you can imagine the user node saves like my name, my address, my date of birth, and so on and so forth. But I'm also saving there what has just happened in this interaction, right? The question that I asked, the information we extracted, the conclusion of my interaction. And we're doing that with another worker. So the maintainer worker will travel to the corresponding user node to save any interaction, any date, any relevant context information that we want to save, so that it's forever there, right? And one useful piece we're saving is the where is it? Oh, is so this is the user node, right? There's a lot of stuff, but I want to kind of highlight the abilities here. So start conversation. So this ability is triggered by the talker worker. If you remember, the talker worker is the main way to ask questions, right? The talker worker actually goes to the user node based on the user ID, the ID of the user that asks the question. They go to the user node first for every request to be able to initialize the context for the worker. So this is where we'll fetch any information we retained previously in previous turns, as well as initialize the state that this incoming question should start at. So in this example, right? So if I'm in the question, oh, order me an Uber, I'm going to be late for work, I'm going to end up at the Uber state, but my conversation hasn't finished yet, because I need to tell the Uber where I need to go. I need to confirm they actually want to order an Uber. So that's why there's a follow-up state. So when the next request comes in from the same user, we want to start where they left off, right? So we're saving that information in the user node, and then through the start conv ability that are triggered by the talker worker, we're going to initialize all of that and set the starting state to be where I left off, right? So that when we do the classification, we will be doing the classification within the context of the node that I'm currently at. So what I mean by that, right? So when you're at root, the scope of classification is different than when I'm at a specific state. So when I'm at root, I need to classify. What I need to worry about when I'm classifying is all the capabilities, right? Weather, direction, Uber. But when I'm already at the Uber state, I don't need to necessarily worry about weather and direction now, because more likely than not, the next question, the next answer, or the next command coming from the user are going to be specific to what this Uber interaction requires, right? So imagine I'm at Uber, and as I say, order me Uber, and then the bot respond, oh, that sure, I can order you an Uber. Where would you want to go, right? At that point, I'm not going to ask about weather. I'm not going to ask about directions. I'm going to tell you, oh, I need to go to the university campus, right? So based on which stage you're at, contextually, you may want to apply different AI models and or apply them differently, right? So in this case, maybe we'll invoke a different entity extraction engine that are focused on the destination location, or we'll do a different classification engine that just trying to figure out if you actually want to go down this Uber path, or you're done with it, you only want to do something else, right? So it's very important to remember where the user left off, and that's where we're saving this last conversation state in the user node. And then when the next request comes in, we go to the user node first to grab where I should start and start this next request on that state, as opposed to always starting at root. So that start conversation. So update conversation. This is what triggered. This is what will trigger by this maintainer worker. That essentially
just super quick. First of all, that's so brilliant, dude. I mean, it's so fun to watch how you solved problems using Jac and Eldon. That goes directly to something we were talking about yesterday, which was, how do you keep that walker state? Do you keep it in the client side? We were talking about that yield functionality, which would be less good than what Yiping just talked about. So that I think that's brilliant, Yiping. That's super cool. Right?
That's really elegant.
Yeah, thanks. Really elegant. Yeah.
Yeah, thank you for that. So the update conversation ability triggered by the maintainer. That's where saving a lot of stuff. And I do want to mention this init user ability, right? So this is triggered by init water, and this is where we essentially populate the profile or the user specific data, right? So I'm mentioning this also mostly, Sean, for your purpose, right? So one of the things we need to do for HLP is taking their the data that they provided, right? So you can see now it's a stub JSON that I put it out of my ass, right? So we will need to update this to at first pull from their JSON, and eventually this is where you will talk to their API or any other customer's API to fetch to directly fetch the user data, right? So it's very modular and contained in this place. So that's user management. I'm going to rest with the rest of it relatively quickly. I mean, this is the main piece. This is where I think a lot of the complexity is, and if hopefully I did good enough job that people can follow, and if you can follow, you'll be able to trace and figure out the rest of the graph. So I do want to quickly touch on this multimodal conversational AI architecture idea. So so far what we've been talking about is this multi-turn, context retention, sophisticated conversational AI architecture. What also exists in the graph that are in parallel is this FAQ architecture. So this is where we're using the scraper and summarizer that Sean and Ashish built, where we can inject answers and answer band from URL or from website or from articles, and they coexist in the same graph, and but they can have different logic, and they can interact with each other with the traditional type of conversation architecture that we just talked about, right? So what's unique about this one is there's a couple of different workers. So there's the seek answer worker that are also triggered on talker, by the way. So the worker logic doesn't need to change at all. So the talker worker are still the simple two-liners that we had earlier, but based on the node you're at, we're triggering different abilities, right? So instead of the listen, plan, think, speed, cleanup that we had earlier, for FAQ, we just have a seek answer that find the right, FAQ answer based on the question. And then we also have these read URL and clean answer database ability that are triggered by the read worker and forget worker. So the read worker is, taking a URL, and it will call the scraper / summarizer API, and then populate all of these answer states, right? And then for that, we'll clean that up. So this is just an example of how you can have different type of conversational architecture in one unified that you can leverage to serve one unified experience interface, and with the same worker logic. Right, it's the same talker worker, but it's triggering different ability depending on the type of node you're at. And then there's this is a pretty important piece, is as part of this, we're also integrating, we also have these AI engine nodes that are also connected to the root. And so each engine has its own special node that are connected to the root, to the graph root, and it has all these abilities. It's maybe hard to see, but once you get into code, you pretty easily parse what each one of these things do. But so this is how you'll be able to train, eval, test, and deploy your AI models all within Jac. You never need to leave JSCTL. You can do this all programmatically through Jac as well if you want. As a matter of fact, as part of our init worker, that will trigger load model, we're loading the correct model that we already trained and ready to go as all part of the Jac program initialization, right? So, and we have all these various other workers trained train the model, save the model, use it to infer. You can use this through GSCTL to just play with the model. We're actually doing that a lot when we were, rushing for this, for the HLP demo over the weekend. You can also train and evaluate it, and this will give you accuracy. You can give it the evaluation data sets, and you can also run set of regression tests, right? So this is really how to design this is very flexible, right? This is just one way that I've designed it that you can use to interact with your AI models. But the point here is having these AI engines integrated into your graph with the rest of your conversational AI architecture, make it really easy to made it really easy during development. Now, this is one of the things that I was like, dragging my feet on and not doing for a while. And every time Jason's like, did you have the training water yet? I'm like, no, why do I need to do this? But once I've done it, being able to, because like as you're building your program, right, you don't want to have to do a lot of context switching, right? Especially towards the tail end of your development, you're going to be fixing, conversational logic at 1 second and then tweaking your data another second. You don't want to have to like, oh, now I need to open up VS Code and touch the JSON file and then call an API through Postman or anything. Like being able to do all of that and test everything all through one interface, it's really, really convenient and really, really nice. So this is kind of why we integrate the models as part of the graph. I just have two more slides and then we're done. So I also want to touch on kind of the testing setup, right? So the Jac programming language actually has a pretty fully fledged kind of unit testing infrastructure with this test and with by water syntax. So we actually built this generic kind of testing generic tests that essentially read from a JSON file. In the JSON file, you specify the flow of conversation you want to test, right? So and then the test will just load the JSON file and run through each one of this question and make sure at every turn the program is processing and responding correctly. So this is in place, right? So as a matter of fact, this test prop, when you're using this to build for your use case, this test probably don't need to change. All you need to do is just change the JSON file to put in the specific question and answer you want to support. And the last piece is the graph definition initialization. So the initialization of the program is essentially done in 2 steps. We first have this graph spawn block. I know it's pretty small, so you might not be able to see, but this is where we're specifying all the nodes and how they're connected together, right? So the main conversation flow. So what's possible at what state? Like at root, you can go to weather, direction, and Uber. And Uber, you can only go to confirm or cancel. Like that definition is encapsulated in this static graph block. It's, right now we're using spawn. You can also use dot for this. Both are kind of interchangeable. And once the graph is initialized statically, we then launch a init water. And this init water bears a lot of the same design principle as the total water, in that the init water has barely any logic. All it does is just travel from node to node. And as you've seen a little bit earlier, each node, if it needs initialization logic, you will have a specific node ability that will be triggered upon the entry of the init water. So the example is the user. I'll just go back real quick. So right, for the user node, they have this init user ability that are triggered on init entry. So upon initialization, the init water will get to the user, and the user is like, okay, I need to go fetch my data, right? So so this is how, why the init water has barely any logic. You just all you can see here is it spawned a few nodes, and then it traversed to the node that we think it needs initialization, that has nodability that are associated with initialization. So those are the main kind of pieces. I'm trying to go kind of breadth first, and then go into a little bit details on the conversational side. There's a couple of other interesting noteworthy bits. I will just put it here as leave here as reference. So we also have a globals .Jac that define a lot of global variables and constants. One thing that's worth mentioning is we're defining intent labels also as global constant like this. The reason for this is because of the type of classification engine we're using, like BiEncoder, which not only relies on the specific question or the input, but the label also matters. By using globals and define those labels to be constant, we're able to very rapidly experiment with different type of intent labels without having to do search and replace and go into the actual graph definition and change the labels that are stored on the edges. One thing I didn't show is the read and forget water that you can use to inject and clean FAQ answers from URL using the summarization engine. And once you dive into the node and state specific logic, we also have specialized classifier engine that use different ones depending on the node and state we're at. At some node we're using the BiEncoder, at some node we're actually using USC encoder, at some other node we're actually using USC2A, just depending on the use case, right? All of that is in the it's all within the node abilities. And I mentioned this, you're able to load, train, and ready to go AI models in Jac as part of the init water. Some quick kind of future work improvements that we already thought of. The first one is node inheritance, right? So as you can probably tell, the conversation state and FAQ state, they share a lot of the same signature, right? So they can benefit from inheritance. The AI model node. So right now we have one for BiEncoder, one for Flare NER, one for Transformer NER. They have all the same waters and the same node. They have all the same node abilities. So they can, but they're the code are duplicated. So they can definitely benefit from inheritance. The other thing that we need to we're going to implement next is be able to cache our embedding in a better way. So right now we're caching our embedding basically at the node or edges that the text exists, right? So intent, if you go back to this, right? So for each one of this intent transition, we're saving the embedding of that intent label at the edge, which is good, but then it's not optimal because some edges may share the same intent. You don't want to store, you don't want to duplicate the embedding if they share the exact same intent, right? So I do have this, you go back to the original, we have this embedding cache kind of module that's not fully built out. But this is, a place we can imagine this being like a central repository of any embeddings of any text. And then throughout the graph, you just go there to fetch and update any embedding that you need, right? And then one of the things that I think will be really cool to do is, so right now for training, we're loading from a file, right? When we're training model, we're loading from a file, which you can pass in through the water. What will be really, really cool is if you can actually embed the training data locally to each node and edge, right? And make it contextually so that when you're training, you don't even need to pass in the file. You just tell the water, hey, I need to train the classifier at this node, and the water will go to that node, grab all the data, and then train it, and then maybe store a link to that ID or a link or reference to the trained model at that node, so that when the water gets to their next, you'll know, oh, this is the model I trained next. I should continue training on it, or I should use that, right? Right now it's still one model through training file, test file, eval file, but this is one of the things that I think will be really cool if we can add. And that's all. So So we have two places where, the code exists. The first one is the CannoniCai code base. So this is in this public repo. And so this one is slightly out of date compared to what I was talking about today, because we made a lot of like improvements on this way to HLP delivery. So if you want to look at things, the latest one now, you will need to go to this specific private HLP branch and repo. I can add you if you want to see. But what I'm going to do in the next few days, actually update what's in the CannoniCai, the public one, basically strip out an HLP specific information so that this is up to date and, as like a reference for everyone. So that's everything.
Yeah,
that's everything.
That was awesome. Wow. That was awesome. Oh my gosh. So yeah, that was so good.
Oh, thank you.
Katrin, Eldon, do you think it's okay if we push the next meeting 15 minutes or 30 minutes?